Um, so today we're going to talk about a brief introduction into triple point, talk about an overview of the lagoon ammonia problem, why its ammonia limits are being placed on lagoon systems, the basics of ammonia removal within a lagoon, and then look at some of the alternatives that are available to help to obviously upgrade your lagoon to meet an ammonia limit. So as some of you probably know, triple point, we believe that lagoons do it better. And we know this is not the conventional wisdom, that there are a lot of people in the engineering community and other regulators and such who in the past years kind of felt like lagoons were old technology and they would end up being replaced as new nutrient limits came into effect. Well, what we really think that you can upgrade a lagoon system to meet any limit, ammonia, total nitrogen, phosphorus, low BOD limits, with the correct equipment in place, and that ultimately upgrading a lagoon rather than replacing it is the most cost-effective from a capital cost point of view, but also from an O&M cost point of view, because lagoons are the simplest wastewater treatment process that is available on the market. So in that vein, we've developed a sort of suite of solutions. We have a lagoon aeration system, our MARS system, which I presented on the webinar previously. We have our nitrox, which I'll talk a little bit about today as it pertains to lagoon ammonia removal. Our nitrox plus D, which is total nitrogen removal. And then finally our PhosBox, which is a tertiary phosphorus filtration system for lagoons to help you meet low phosphorus limits. So we feel like whatever your limit is, we can treat it and we can get it your effluent down to whatever level it needs to be at. In this vein, we believe in education, and we want to take this Lagoons Do It Better concept and help people to understand that they can do it, and that lagoons are a very cost-effective solution. And so in that vein, we have informational blogs online. We blog every 2 weeks. It's very popular. People like reading it. We have educational videos. We have a YouTube channel that you can find as well. And we do training events, both on-site training events where we actually bring in a speaker, a lagoon expert who's a lagoon operations expert, to do training for operators. So, for example, we did 4 days of training, 2 days in Iowa and 2 days in Missouri at the beginning of May. But we also have a training coming up in Talladega, Alabama, in October 15th. So if you receive our emails, you'll see us promoting that here very shortly. But we also do these webinars, and this is actually a relatively newer thing, hence the technical difficulties that we had here at the beginning. This is only our second webinar, so I do apologize, but we will be rectifying these, and this won't be an issue going forward. I can promise you that. And the other thing we do is we have a Facebook group, and we try to connect operators with operators, or engineers with engineers who engineer lagoon systems, so we can kind of pool the collective knowledge of everybody in the country or even in the world so that we can help each other make lagoons do it better. So you can go to our website, tpenb.com/LDIB for Lagoons Do It Better for more information on all of these resources that we offer. And to also register, and if you register, we'll send you a free hat, a free Lagoons Do It Better camel hat, as you can see there on the screen. One of the things I'll mention here is we are going to redo our Fundamentals of Lagoon Aeration webinar just due to popular demand. So if you weren't able to make it last time, we will be hosting it again on July 11th, and so an email will be going on about that very shortly here. I'll be doing it again, and I think it's a good webinar. We got a lot of good feedback. People really enjoyed it. So, what is ammonia? Well, ammonia is a compound of nitrogen and hydrogen. In its sort of native form, it's a gas with a putrid smell. So, cat urine smells like ammonia, when you smell it. When it gets into water, most of it becomes ionized ammonia, or NH4, but some of it still remains in its gas form, NH3. So these are the two components, ammonia, which is NH3, and ammonium, which is NH4, which is the liquid form of ammonia. Now, when it comes to the sort of nitrogen cycle, or the nitrogen, components of nitrogen, NH3 and NH4 make up ammonia nitrogen total together, and then you've got nitrite and nitrate, which I'll talk about. And what we're talking about in this presentation is nitrification. So that's taking the NH3 and converting it into nitrate. Obviously, I'll get more detail. And then you have organic nitrogen. So these things together make up total nitrogen. So if you ever have a total nitrogen limit, this is what you need to think about. It's a sum of your ammonia nitrogen, your nitrate, and organic nitrogen together. The other category that you often see is TKN, or total Kensington nitrogen, and that's the sum of ammonia nitrogen and organic nitrogen together. And then finally, you have what's known as total inorganic nitrogen, which is the combination between ammonia nitrogen and just nitrite and nitrate. So, all these different categories of nitrogen can be kind of confusing, and when we started doing this, getting into ammonia treatment and nitrogen in general, I sort of created this sort of slide to kind of give myself an understanding of how this all fits together, and this is kind of how it shows it to you here. So ammonia, where does it come from? I mean, there's a lot of different sources of ammonia in municipal wastewater. It's mainly human urine. So I'll give you an example. We've worked on a few truck stops in the past, and truck stops tend to have a much higher level of influent ammonia than a typical municipal system, where you have your showers and washing machines and things like that are diluting it down a little bit. So that's a big human source, but there are industrial sources of this. We're working with some industrial, fertilizer manufacturers that have, nitrate and ammonia in their water because that's what they produce at their site. So that's a very common place you'd find ammonia, and just food processing in general. You get ammonia as part of that process. Sometimes they use ammonia as cleaning agents, to clean tanks and things like that. You often see, for example, Windex or window cleaner is like pure ammonia as well. So why is ammonia being regulated? Well, ammonia being regulated because it's very toxic to the amphibious life once it gets into a waterway. So it literally is like a bullet in the head to a lot of fish species that you'll find in our country's waterways. And so it can worst case scenario, it can cause obviously fish kills, but there's lesser cases of worse, which is just the fish are more aggravated, they don't grow as much, they don't reproduce as much, it depletes fish stocks, things like that, because it just has a toxic impact upon that food chain, including the fish directly on the fish themselves. So, if you look at a lot of lagoon systems, and this is showing you the Midwest of the United States, but there are lagoons literally in every watershed within the United States practically. But to give you an example, in the Midwest, there's probably maybe 3,000 lagoons or so, 6,000 lagoons nationwide, and all of the water in the Mississippi watershed, coming from our wastewater plants, coming from our industrial facilities, obviously comes down into the Mississippi and eventually into the Gulf of Mexico. So the Gulf of Mexico kind of being the nation's toilet, so to speak, when you consider it from a pollution point of view. Now, you may not think that's a lot of nutrient pollution, especially when you consider it from a municipal lagoon point of view. So you may not think it's a lot of pollution, but you'd be surprised how much it can actually amount to. So this slide you see here that, if we assume there's 3,000 lagoons within the Mississippi watershed, right? And we assume that in the wintertime, these lagoons fail to treat for ammonia, which most lagoons aren't very good at it. And so you're putting out 40 milligrams per liter of ammonia, and on average 300,000 gallons a day per facility. Well, if you add all that up, and it comes up to about 300,000 pounds of ammonia that are finding its way into the Gulf of Mexico per day for 3 months of the year during the winter when lagoons really fail to treat ammonia. So, that's a lot. 300,000 pounds of anything ends up being quite a mass. Now, I don't know if this pile of dung here is 300,000 pounds, but it's certainly a lot of ammonia. So it does amount to something, and when it finds its way into the Gulf of Mexico, it does create a condition in which you have what we call a dead zone. And it's not just ammonia that's causing this dead zone, but ammonia is a participant in it in terms of, like I said, being toxic to amphibious life, but, nitrates and nitrates and phosphorus also cause this. So, hang on one second. So when you add all these nutrients together, it really does create an environmental impact on all sorts of different waterways and ultimately on the Gulf of Mexico. So that's why ammonia is being regulated. That's why nutrients in general are being regulated by the EPA, and that's why it's such a hot topic because of the environmental impacts of these things. So how do we get rid of ammonia? Well, we do this by a process called nitrification. Now, nitrification, there are other ways to get to pathways to removing ammonia from wastewater, such as ammonia stripping, use an ammonia stripping tower. But in municipal wastewater, nitrification tends to be the approach that's taken. It tends to be the most cost-effective approach. Really the ammonia stripping towers of the world, things like that, tend to only be used when you have a lot of ammonia, when you have like 300 milligrams per liter or 500 milligrams per liter. That's when it tends to be cost effective. But if you're down at lower levels, under 100 milligrams per liter, generally speaking, nitrification makes sense. So ammonia, when you're getting rid of ammonia using nitrification, you are converting the ammonia first into nitrite and then into nitrate. And you do that with a special type of bacteria, collectively known as nitrifiers. Nitrosomonas and nitrosbacter are the two bugs that you're looking to foster in order to accomplish this task. So within the scope of a wastewater system, you typically have two different types of bugs. You have what you call the heterotrophic BOD-consuming bacteria and the autotrophic nitrifying bacteria. Now, the heterotrophic bacteria are, very hardy, less sensitive to conditions they find themselves in, will, eat a lot of waste BOD, basically, in cold temperatures even, and just in general are able to outcompete the autotrophic bacteria for the oxygen and the food within the water column, right? So the nitrifiers are way more sensitive to these conditions. They're way more sensitive to temperature, for example. They're way more sensitive to dissolved oxygen levels, and in general are not able to effectively do their job unless you create specific conditions for them to do it. So the name of the game when you're trying to nitrify within a lagoon is how do we create these conditions, right? If we can create these conditions, we can accomplish the nitrification even at cold temperatures. So I've identified 6 key factors, right, that I've seen within lagoon systems that municipal lagoon systems particularly, but it does apply to industrial as well. 6 key factors that you need to look at when you're trying to get rid of ammonia. Number 1 is BOD. So these heterotrophic bacteria are going to outcompete the autotrophic bacteria for food and oxygen. So you've got to deplete the level of food that they have, the BOD that they have, right? And once you've depleted that sufficiently, okay, then you can begin to nitrify. You can begin to grow those nitrifying bacteria. Okay, so generally speaking, that's around 20 to 30 milligrams per liter within a lagoon system. So that's job 1. Number 2 is you've got to provide sufficient oxygen for the nitrifying bacteria. Okay, nitrifiers require, the heterotrophic bacteria require 1.5 to 2 pounds of oxygen per pound of BOD coming in, right? And then you want to keep the dissolved oxygen level high enough, right, that you have a little bit of buffer in there, and that can be anything from 0.5 milligrams per liter of dissolved oxygen to 3 milligrams per liter of dissolved oxygen, depending on where you want to run it. For nitrifying bacteria, the autotrophs, they want 4.6 pounds of oxygen per pound of ammonia coming in, and they want to see DOs up in the 6 to 8 kind of range from a residual dissolved oxygen level point of view. So that's significantly more oxygen. And so if you don't have that natively within your system currently, you're not putting that level of oxygen in the water, then you're not going to nitrify. And that's a big, big reason for it. So these bugs really do consume a lot of oxygen. They want to have high oxygen conditions in order to nitrify, but especially in colder temperatures. And the other thing about aeration, which is I touched on this in my last presentation, is the importance of mixing, right? If you do not get mixing, the purpose of mixing is to get the bacteria, the oxygen, and the food, the waste, all mixed up together. If you don't accomplish that task, right, you can put all the oxygen in there into a lagoon that you want. You can roll up to a lagoon with a tanker load of pure oxygen and pump it into a lagoon. If you don't mix it, that oxygen's going to be wasted, right? Because the bugs got to have access to the food and the oxygen in one spot. So mixing, again, is so critical to the overall process in wastewater that any aeration system has to be able to mix in addition to adding oxygen. The third thing is alkalinity and pH. So you will actually consume alkalinity during the nitrification process. So it is very, very common to see that if you're going into a nitrification system with 7.5 pH, you'll come out of it with 7 pH or 6 pH or something much lower than not much lower, but fairly lower, because the nitrifiers will actually consume that alkalinity during that process. So generally speaking, we recommend about a neutral pH, in order to get nitrification going. If it's a little bit higher or a little bit lower, the bugs don't like it. They don't like they like a neutral pH to start with, but there definitely has to be sufficient alkalinity within the water column to get the job done. The fourth thing is you've got to grow nitrifiers. If you're going to nitrify, you're going to have nitrifiers. Makes sense, right? So nitrifiers are what we call attached growth organisms. They want to grow on a substrate of some kind, right? They want a home to live. So you've got to give them that surface area to grow on. If you give them, the more surface area you give them, the more nitrifiers you're going to grow. The more nitrifiers you grow, the more nitrification you can achieve at cold temperatures. So ordinarily within a lagoon, it's actually fairly common to see some nitrification happening if you've got aeration in your lagoon system. And that's because the nitrifiers are growing on the baffle curtains, they're growing on the walls of the lagoon, or on the floor, or on the aerators. They're growing on whatever they can get their hands on, to attach themselves to. And so the problem with that, of course, is that sometimes if you have a lot of ammonia, or if you obviously in a colder climate, you can really, really struggle to nitrify in the winter months, which tends to be mostly the problem. So, as it pertains to that temperature, here's an example for you. this was a facility that actually we're constructing a nitrox for, or nitrox is under construction currently, where I took 2 years of their effluent data, and I had effluent temperature and I had effluent ammonia, so it was quite useful data to have. And as you would expect, as I would expect to see, when the temperature is high, the ammonia is low, right? And when the temperature is low, the ammonia is high, because the nitrifiers, the autotrophs, they don't like cold temperatures. They slow down. I mean, all biological activity slows down in colder temperatures, but the nitrifiers slow down very, very quickly in cold temperatures. And so this is where a lot of lagoons struggle to nitrify consistently. It's because they have 2-3 months a year where they've got colder temperatures and they're not able to meet their limit. That red line down there shows you kind of what a limit would be, a fairly low ammonia limit for a lagoon would be, but what it would be nonetheless. So, to recap, lagoons actually can, treat BOD fairly well. Most lagoons are putting out under 30 milligrams per liter right now in terms of their BOD, so that doesn't tend to be a problem for lagoons. They have sufficient pH, unless you're in a really weird situation. If you have an industrial process, you might not have sufficient pH and alkalinity, but they don't have an issue with that, generally speaking, or you can correct for that relatively easily. The third thing is most lagoons don't have any heavy metals or toxins. I didn't talk about this because it's not something I run into a lot, but they don't have the kind of biological inhibitors within the water that would stop nitrifiers from growing. The problem with lagoons is that they do not have enough nitrifiers. They get cold in the wintertime, and they do not have enough aeration and mixing within the lagoon. So that's a big issue, and that's why lagoons fail to nitrify. Briefly. So I'm going to look at a couple different options on how to tackle this situation. First of all, I'm going to look at, obviously briefly look at going to a mechanical plant, which is something that, generally speaking, is considered quite frequently when you get a nutrient limit of some kind like ammonia. I'm going to look at a modified discharge briefly, and then I'm going to look at 3 or 4 process upgrades. So how do you take a lagoon and kind of retrofit it to help it meet an ammonia limit? So mechanical plant. Now the pros of a mechanical plant, and this shows fairly complicated and large mechanical plant on the screen there. Typically I wouldn't necessarily, not for the systems that have lagoons, don't have this high of a flow to have this complicated of a mechanical plant, but nonetheless you can kind of get the idea. The good things about mechanical plants is they can reliably meet ammonia limits. I mean, they've been doing it for a long time. It's very proven, well understood technology. You can increase the treatment capacity within a very small footprint. So if you have a lagoon, lagoons take up a lot of space. So usually if you put a mechanical plant down, you can maybe double or triple the treatment capacity within the same footprint, which might be helpful for communities that are growing very quickly, and where there's maybe no other option. And then, finally, like I said, a small footprint. So those are the pros. I think on the con side, it's fairly expensive to build a mechanical plant. High capital costs. Typical lagoon upgrade, you're looking at $5 to $10 million. It's kind of what I've seen, if not north of that, depending on the flows. Once you get the mechanical plant in place, the operational complexity goes up exponentially, because nothing is simpler to operate than a lagoon system. If you have a non-aerated lagoon currently, I mean, literally you're pumping water into a lagoon, which is a hole in the ground, and you're letting it sit there for 90 days, and then it's just hydraulically flowing out. So there's just nothing to do there. If you have aeration, yes, you got to maintain your aeration system, but it's not that much aeration in comparison to a mechanical plant. So when you go to a mechanical plant, it really does. The number of components jumps up significantly. The amount of maintenance and jumps up significantly. The operational complexity jumps up significantly. It really does add a lot. And not only does this cost more from an operational point of view, but it also requires more manpower. And so for a lot of the communities, and I've seen this more and more, they're not even considering really a mechanical plant option. Most of them write it off pretty quickly because they realize that this is just not feasible. The average lagoon operator currently is the dog catcher in the town. He snow plows the streets in the wintertime. He mows the parks in the summertime. Like, he's wearing a lot of hats. And so to ask him to try and operate a mechanical plant is a big ask, and maybe not the most feasible option for the city. The other thing you can do, and this is sort of a non-ammonia treatment solution, but you can modify your discharge. So you could go to land application, you could build storage lagoons and do seasonal discharge. You also need to build storage lagoons for land application, and you could look at constructed wetlands. So I'm not going to dig into these too much because they're not really a treatment options, really. But, I would say land application requires storage lagoons. Seasonal discharge requires storage lagoons. That requires extra land. So that's, the first thing to figuring out the feasibility of that is, can you get the extra land, number one, and is it feasible to buy it adjacent land, for example, and build storage lagoons, because you're not going to be discharging continuously, right? And you can only discharge if you're land applying for half the year, let's say, and if you're seasonal discharging twice a year in the spring and the fall. And so that's a big expense. And I would say when it comes to the land application side, I in a previous life I worked for an engineering firm that designed a lot of land application systems, and they're kind of environmentally friendly in a lot of ways, but they're not the easiest thing to operate. It's not like it's just you have to maintain an irrigation system, right? And you can get clogged irrigation heads, you can get pump issues, if you got a center pivot rig, you get track issues. It's not a slam dunk easy operation situation. It might be the best situation, but it's not necessarily that straightforward. So I just caution people when they're looking at that kind of thing, thinking that it's just easy. It's not. It does require a lot of work, and you get a lot of planning. You've got to get rid of the water every single year. You got to maintain the equipment. The constructed wetlands is a good option. Requires a lot of land again. It may only be feasible more in the southern part of the places with warmer climates, not really the cold climates, just because obviously things will die in the wintertime in colder climates. So those are options. I didn't talk about them too much, but something worth noting. So I'm going to consider four, like I said, what I said was sort of process upgrades. How do we take this lagoon, right, add something to it, right, leverage that existing infrastructure in order to meet the ammonia limit? So the first one I'm going to look at is, and this kind of goes back to what I talked about, and one of the factors is if you want to grow nitrifiers, you got to give them a place to live. So what a lot of people, a few companies have done is come up with an idea of, well, how do we put surface area within the lagoon to give the nitrifiers a home? And so what they came up with were these sort of media cages, right? And these media cages within them have lots of, and this one picture here shows a fabric type of media, but there's also plastic media cages, and you drop these things into a lagoon. It's like a module, and it's got aeration underneath it to provide the oxygen and mixing, and it just drops to the bottom, and you goes through the lagoon, and you're hoping you're going to get your nitrification, right? Because you're going to grow the nitrifiers on that surface area. Now, I think, Prima Facie looked at something like this when we were developing our nitrox system before we developed it and got into it, because we saw this out there. We're like, well, this makes sense. Just drop it in, right? Simple. So I think there's potentially, benefits of low capital costs, no extra lands required. You're just dropping them into the lagoon, easy operations, and all those factors. I think the downside, and kind of what we saw with the data from the field, was lagoons are very, very big bodies of water, right? And so if you're dropping these media modules in, how can you guarantee that the water passes through the media module? Because it's, if it doesn't pass through there, it's not going to get in contact with the nitrifiers. And if it doesn't get in contact with the nitrifiers, you're not going to get the nitrification you need to take that ammonia out to meet your limit, right? So, lagoons have been well known to have short-circuiting issues where the water is going to go, around, not follow the right path that you want it to follow, in essence. So the water could short circuit through, over, above the medium nodules, around the medium nodules, might not necessarily get fully nitrified. And so I think what happens is, when what I've seen, the capital cost is that you end up having to put more surface area in there because you're trying to have a safety factor for the short circuiting that might occur. And so you end up having to put a lot of medium modules in there, and it drives up the cost. So it doesn't always end up being the most cost-effective thing, even though at first blush it might seem that way. The second thing that we saw with these medium modules was, we talked to operators and sites where they had them, and for the first couple of years they worked great. And then it got to like year 2, and all of a sudden it's like nothing. Nitrification completely drops off over the course of 3 months. And 2 things had happened. Number one, some of them got clogged with just debris, with biomass, with whatever that finds its way into a lagoon. And the second thing that happened was they had redworms that were growing on the media itself, and the redworms were actually eating the nitrifiers, and that's what happens. And so they, really didn't find a way to overcome that in a lot of cases. And you don't get redworms at every lagoon site, but it's certainly something you can see. So there's always that risk of that occurring. So I think the other thing, and probably the most important thing, maybe for all of these reasons, this is some data here from a company that makes a media module, drop-in media module like this. And as you can see, it does a pretty good job in the summertime of treating the ammonia, but it really did struggle in the wintertime to maintain consistent low ammonia levels. And so it depends on what your permit is, obviously, but a lot of the permits we've been seeing, ammonia is under 5, is fairly typical if you get an ammonia limit, and you might struggle to get this done using a drop-in media module. This second technology that we're going to look at is an aerated rock filter. So rock filters for lagoons have been around for a long time, actually. They're very common in Illinois, for example. They put a lot of rock filters at the back of lagoon systems and, right around the discharge, the effluent pipe. And they were originally conceived as a way of minimizing algae growth and minimizing basically TSS getting out of your effluent pipe. Now this is kind of similar. It goes at the back of your plant, but instead of being in the lagoon, it's sort of a separate basin all in and of itself. And it's a hole in the ground with rocks in it, and then you've got coarse bubble aeration grid on the bottom, which is bubbling air from the bottom to the top, and the thing is submerged, right? So there's water throughout the whole thing. And what happens is the nitrifiers use the rocks as their attached growth sites. So it really, the more surface area you have, the more nitrifiers you grow, the colder you can accomplish this nitrification. So they all grow on these rocks, and what this has been proven is that even at very, very cold temperatures, this technology was actually developed in Canada, where obviously it gets colder. I mean, colder than anywhere else. I mean, maybe you go to the Arctic, go north, but just as cold as that in the wintertime. And so even though the nitrifiers are slowing down, and when it gets colder and the water temperature gets colder, because you have so much surface area on these rocks, you're able to overcome that low temperature by having a lot of nitrifiers, right? So this technology is very proven in cold temp. It leverages the existing lagoon infrastructure. It's very simple from an operations point of view. You've got a blower sitting on shore that you got to maintain, just like anything. But if you're going to nitrify, you're going to have some kind of air input, some kind of motor to do that. So that's the name of the game. And it's been around for probably 15 plus years now, and been doing this job fairly well. I think some of the downsides that I've seen, and just talking to engineers and who do facility plans and compare these different technologies, is this system tends to have a fairly high capital cost. Sometimes you do need to buy land in order to fit the system. It won't fit within the existing lagoon site. But these cells, these rock filter cells, tend to be fairly big. And so maybe they're 1/3 the size of the existing lagoons that are there. And so they take up a lot of space, and then just the general construction costs tend to be fairly high just because these things are big. You need a lot of rock to bring in, and so forth. So that's probably the biggest concern that a lot of people express about the system. The second thing would be that it's a rock filter, it's an aerated rock filter, and as with all filters, most filters have the ability to backwash themselves, right? Because you've got a fixed media that's in there in the rocks, and what we know from lagoons and our lagoon experience is that over time you're going to build up sludge within a lagoon, because that's just that's where you store your biosolids, and you get turnover in the spring and the fall. And as you get turnover, that kicks up BOD and TSS into the water column, which then will travel through into this rock filter, and so it has the potential to clog it. And there's no ability. This rock filter doesn't have the ability to backwash itself. So there's a potential long-term concern there that eventually that the rock filter could get plugged. So that's just a concern that I hear from people on the outside. The third process we're going to look at briefly is actually putting insulated covers on the lagoons. So, as we talked about, temperature is a concern. So how do we overcome this temperature aspect? The rock filters overcome it by having lots of surface area. This system overcomes it by not letting the heat from the water that's coming in to escape the water, right? So they put floating insulated covers on it, right, which stop that heat from escaping from the water in the first place. So if they can do that, obviously they can get the nitrification. They can achieve that nitrification. So typically the way this is configured is they put aeration in. They have an aerated, a highly aerated first cell, partially aerated second cell, then a polishing cell. All of these are covered. And then they also have a polishing reactor at the back. And the polishing reactor actually has fixed media in it, not rocks, but a plastic fixed media, corrugated plastic media, that's in that tank with aeration in order to get nitrification in there as well. So, this approach has been around a while. It's proven that it can get the job done. They have a decent number of installations within the United States that prove its capabilities. However, I think, some of the downfalls I hear from people are, the covers are expensive. Lagoons are big bodies of water, so you're end up paying a lot for covers. To cover them, it's about $350 a square foot, just for a quick calculation. So you can easily spend $500,000 or $750,000 just on the cover before you even get into aeration equipment and the polishing reactor. The second thing is, with a lot of the aeration in the first cell, with the highly mixed in the first cell, partial mixed in the second cell, you end up with a lot of aeration equipment to maintain, and you can't see that aeration equipment because it's underneath the cover, right? So a lot of people complain, it's like, I don't know how it's working because I can't even see it, and the only way you can see it is if you get out there, you can open a hatch you can actually walk on these covers. You can open a hatch on the cover and take a look. But then, of course, you got to pull up and maintain that equipment at that point. So, and a lot of people are really not comfortable walking on these covers, even though it's apparently perfectly safe. I don't have a lot of experience myself, but from what I hear, that they're designed to be walked on to some extent. So that's a big concern, and it makes maintenance difficult. It makes monitoring of the operation difficult. And so some people are just sort of a little uneasy about that. And then the covers themselves are not maintenance free. If you don't maintain a cover, you can get growth on it, you'll get grass growing on it, you'll get all sorts of plants and vegetation growing on it, and so you got to get out there and maintain it, and it will break down over time. Just like anything that's exposed to the elements, in 10, 15 years, you're going to have to replace that cover. And again, when you're talking about a cover that costs $500,000 or $750,000, that's a lot. It's a big expense to be budgeting into the system. And I think, my point of view of it was, when you're looking at this, and this is probably true of the rock filter too, is that you're paying for thermal regulation, which you only need for a month a year, anywhere between a week a year for if you're in Missouri, or 2 weeks a year if you're in Missouri, or if you go north, maybe it's 2 months or 3 months a year. And so it seems kind of crazy. It's like, well, you're paying up front for a temperature issue that only occurs for a limited, period of time every year. So with that in mind, we developed our nitrox system. And what our nitrox is similar to those technologies in terms of trying to leverage that existing lagoon infrastructure as much as possible, because if it ain't broken, don't fix it, right? So we use the first 2 lagoons for BOD removal. Once we get through the second lagoon, we pull out of that through our 2-stage nitrification reactor, which are the tanks there at the front of the screen. 2 concrete tanks is typical design. And then from there into a polishing cell out the discharge. So it's a very small footprint system, and it fits in with pretty much any lagoon site I've ever looked at. And it's fairly low capital cost and easy to maintain. And I'll get into the details here in the upcoming slides. So the first thing with the nitrox system that we do is we use an attached growth media. And this is what's called a moving bed media. And you can see it there. It's little Chex Mix looking things there at the front of the screen. And what this does is it gives the nitrifiers an attached growth site, right? So they go grow on that inner protected surface area within the media itself. And so they're in the tank, and the beauty of the media itself is that you can fit a lot of surface area in a really small footprint. And so the more surface area we have and the small footprint, the more nitrifiers we grow. The more nitrifiers we grow, the faster we can nitrify and the colder temperatures in which we can do it. So to give you an example, a typical lagoon system, like I said, can meet an ammonia limit sometimes in the summertime if it's got aeration in it. In a typical lagoon, if you measure the baffle curtains, measure the sidewalls, the bottom of the lagoon, and you say, all right, well, there's 167,000 square feet, right, of surface area for attached growth nitrifiers at just the lagoon in its native form. You can fit that same amount of square footage into 1/3 of a semi-truck using this type of media. So it really does pack a lot into a small footprint, which allows you to have a smaller reactor, which allows you to have lower construction costs, and allows you to easily fit it within a lagoon site. The next thing about the reactor is we use a medium bubble aeration grid on the bottom of it. So this is a fancy name for a pipe with holes in it, stainless steel pipe with holes in it. So it's a very robust, non-clogging system that also provides a highly mixed environment and a high oxygen environment, which is what we need to get the nitrification done. So the benefits here is all the water that comes into these reactors is highly mixed, does not have any opportunity to settle, so you're not going to settle out any solids. But you also guarantee that all of the water is going through the media where the nitrifiers are, so you get that high level of nitrification through the reactor itself. And then ultimately, the grid itself is very low maintenance, pretty much maintenance free, because it's not a membrane diffuser, it's not fine bubble, it's medium bubble. So it's just a pipe with holes in it, very robust. So you shouldn't have to touch the aeration grid for 20 years. The third aspect of the system, which is really important, is we will actually, we know we can nitrify through our reactor down to 5 degrees C water temperature, or 41 degrees Fahrenheit. So what we will do, and this is what our patent is on in regards to the nitrox, is we will thermally regulate the temperature of the water during the cold winter months. So there might be, depending on where you're located and what kind of northern environment you have, you might have 2 weeks, a week of cold winter temperatures that gets you below 5 degrees C, or you might have 3 months. If you're in Iowa or Canada, where you really have sustained water temperatures below that level. And so what we'll do is we'll actually heat the water up. And we do that by either using an electric, resistive low tank heater, a natural gas heat exchanger, propane heat exchanger, or we can even use geothermal to accomplish this little bit of temperature rise. Now, what's important to realize here is, the benefit of this, of course, is that we can guarantee that nitrification is going to occur because we can guarantee the temperature. But it's also important to realize is, again, it's only a small period of time each year that you have to do this. So this is a graph we put together to kind of give you a sense of the heating costs that are involved, but I'll give you a few examples of what we typically have seen. So 2 facilities that we installed in Missouri, for example, one was 100,000 gallons a day, one was 60,000 gallons a day. We found that, on average, these facilities use about $1,600 for the 60,000 gallons a day facility, which is the Hillcrest facility, and $2,500 a year for the Villages facility. If those are obviously lower flows, we have another site which is higher flow and lower temperature in the city of DeSoto, Iowa, where they are estimating about $15,000 a year to heat that water up. Now, that's money, and this all costs money to do this, but where the nitrox really benefits is that even though it costs a little bit more to heat the water when you need it, right, it's so much lower cost on the front end relative to the alternative systems that life cycle cost over 20 years never really catches up. So you have to borrow less money to build the plant, which means your monthly payment's less to own it, and to pay for the loan back. And so ultimately, you're never going to catch up from a total life cycle cost point of view. The nitrox is going to be a lower cost over the 20-year life cycle. And that's what we've seen consistently in all the facility plans that engineers have looked at the system for. And I think one of the beautiful things about this system is its low operation and maintenance costs, right? So, it's really your operational mandate from the operator's point of view is you got to keep the blower running, which, if you're going to nitrify, you got to have some air source, and if you're going to have some air source, you're going to have some kind of electrical motor, blower, whatever it is to get it going, and that's just the nature of the beast. But, as long as you keep that operational, you change the belts, check the oil, change the air filter out occasionally, you're good to go. And all of that's onshore, easy to access. The second thing is you got to keep the flow going through the reactor. If you don't give the bugs food to eat, they'll die. But for the most part, if we can set it up with a gravity feed system, the gravity feed into the reactor, we can typically see pretty good. That's pretty easy to keep going, because you're just letting it gravity feed in. And the third thing is just the heater. You're going to have to inspect it, clean it once a year, typically in the summer months when you don't need it to be online. You don't need it for temperature regulation. So it's a very, very simple system to operate. It's very similar to operate from from the perspective of it's just like an aerated lagoon. You got a blower, you got to keep that going, you got to keep flow going through the thing. But for the most part, it's very straightforward. So we really feel like this small footprint, low capital costs, low operational complexity, low operating costs, all really lend itself to making a great system for lagoons overall. So just to kind of round this out, I'll give you some costs on this. We have this is a just sort of like a typical lagoon system, 500,000 gallons a day. And I looked at just talking with the engineers and the facility plans that we've seen, and kind of came up with some numbers as to what the different systems would cost in comparison to each other. So we looked at obviously covering the cell, putting in lagoon media in, looking at an aerator rock filter, and then finally our nitrox reactor system. So we looked at the capital costs up front, estimated capital costs, estimated operations costs, and then long-term maintenance as well, and pulling all these numbers together into a long-term life cycle cost. So, the covers were probably the most expensive solution to put in up front. Then you're looking at in-lagoon media, then the aerator rock filter, and then finally our nitrox system. And then when you pen these numbers out and kind of look at them over a 20-year life cycle, this is kind of what I was talking about earlier, was that the nitrox approach is the more cost-effective approach, just because you're saving so much on that upfront capital cost, and your operating cost is not increasing by that much in order to accomplish that. So this is what we've seen, and we've seen this on a pretty consistent basis with the facility plans that we've worked on with consulting engineers for towns and for industries. So we really feel like it's a really good cost-effective option. So just to give you a couple of examples of sites where we've implemented this system, we've got, this one is actually showing the layout of the Hillcrest lagoon system in Missouri. It was a 4-cell lagoon, and in this case they were not able to gravity feed, so they go through the first 2 cells here, actually these 2 cells right here, and then they go into this pump station, and it goes through a force main and gets pumped up into the nitrox system, which then it gravity feeds down into this polishing cell down here, and then ultimately out the discharge. So this system was installed a couple years ago. It's been in operation now for about 1.5 years, almost 2 years. As you can see, very small footprint, very small tanks, very close to the home there. As you can see, we use blower systems that are really quiet and can sit outside, which make it really ideal for really any wastewater plant, but certainly the ones that you're close to homes and people are going to hear it. The blowers, the whole system operates at around 70 decibels, so that's kind of our ambient, speaking, talking to you right now would be about 70 decibels. So it's really hard to even hear which blower's on when you're standing right next to them. You got the complete mixed aeration basins, and then finally goes into the final polishing cell. The numbers we've seen out of this have been excellent, and this is kind of, for me, it's sort of proof that lagoons do it better. I mean, you can see here over the course of this initial testing period, they had, influent ammonia, fairly typical, around 30 milligrams per liter, 25 to 30 milligrams per liter, and they were putting out non-detect ammonia effluent pretty much the whole time. They saw some minor spikes kind of in the winter months that didn't get anywhere near their permit limits in terms of the effluent. So it was really quite very, very successful from an ammonia treatment point of view, but also from a BOD treatment point of view. The nitrox does polish BOD, so we're seeing really excellent numbers, and the water, just looking at it coming out of the effluent pipe, looks excellent. You're getting 200 or so BOD TSS coming in, and we're putting out single digits BOD and TSS going out. So it really is doing a great job. I don't know a lot of mechanical plants that can consistently achieve single digits BOD TSS. So with that, I'll open up to any questions that you all have. If you want to type them in the chat box. Again, I sincerely apologize for the technical difficulties that we had, and we will do everything we can to avoid this issue in future. If anybody's got any questions, please type them in. Okay, apparently not. We will be holding this webinar again tomorrow, so if any of you guys had colleagues that were interested in seeing it, we're going to do it again tomorrow at 11:30. Again, hopefully we can not have any technical difficulties that we had on starting this guy up. But I want to thank you all for coming, and hope you all enjoyed it, and we will speak to you soon. Thanks.